High-energy cosmic neutrinos are incisive probes of particle physics and astrophysics. This becomes apparent when we place all known neutrino sources on a plot of neutrino energy in the horizontal axis and baseline or distance travel from the sources to the detector in the y-axis. Most of what we have learned about neutrino properties and neutrino sources comes from the bottom left corner of this plot. There's a reactor neutrinos, atmospheric neutrinos, solar neutrinos, etc. What I will be talking about today lies in the opposite corner. These are high energy neutrinos of energies from TeV to about 100 PeV and ultra high neutrinos of energies even higher. They are the neutrinos with the highest known energies and the highest energies we expect to detect, which means that they can probe energy scales of physics that are unreachable with current accelerator technology at Earth, and they travel the longest distance, all the way up to the size of the observable universe of a parsec, which means that they are messengers from the most distant astrophysical sources, but also that if we want to test feeble new physics effects that would individually be very difficult to see, these effects could accumulate over the long travel distance and become observable by the time the neutrinos have reached the Earth. Of course, people have realized the potential of high energy neutrinos and also low energy neutrinos to do particle physics and astrophysics, and there's a host of experiments that are being operated currently or are under planning and will turn on in the near future. At the lower energy end of this plot, there are experiments that are targeting the measurement of the oscillation parameters, and there's interesting synergies between what those can do and what we can do at high energies. But we will focus mostly on high energy neutrinos discovered in 2013 by IceCube and currently detected regularly both by IceCube and by other large-scale neutrino telescopes. And even higher energies, we expect to see ultra-high neutrinos, which were first predicted more than 50 years ago, and that we might have already discovered one such neutrino in the KM3-NET neutrino telescope not very long ago. Now, this talk is about flavor. So whereas the energy distribution and the arrival directions and the timing information of astrophysical neutrinos, all of them are interesting observables and carry valuable information to test particle physics and astrophysics, I will focus rather on something unique to the neutrinos, which is the fact that they have flavor and that they're flavorless. Something we have learned from the low energy oscillation experiments, but that affects also high energy astrophysical neutrinos. So with that in mind, let's give you a eagle's eye view of what the physical scenario is. We have a collection of cosmic accelerators distributed in redshift, distances between tens of megaparsecs all the way to tens of gigaparsecs, essentially the size of the observable universe. These accelerators are able to take protons up to the highest energies we have seen so far in excess of 10 to the 20 electron volts. And those protons interact with ambient radiation or ambient matter, create intermediate mesons. Those mesons decay and create high energy neutrinos, which we see after they propagate over billions of light years or so. The most of what we know about high energy astrophysical neutrinos, however, comes not from identified individual point sources of neutrinos, of which we already only know less than a handful, but by studying the diffuse flux of high energy physical neutrinos, which is the collection of contributions of all the neutrino emitters across all the redshifts. So what I will say in the next few slides is coming from those of diffuse. At Earth, there's currently 3 ongoing large-scale neutrino telescopes. IceCube is the biggest one in Antarctica. KM3-NET is in a major North Sea, and Baikal GBD is in Lake Baikal in Russia. IceCube is already 1 kilometer in size. KM3-NET and Baikal, once completed, will be about the same size. So they will have comparable. IceCube and the other 2 detectors see mostly 2 kinds of events. And here flavor starts to become more relevant. Showers, which are made mainly by nu and nu tau, and these are light topologies where a neutrino interacts somewhere in the ice. The ice is instrumented with strings that contain photomultipliers to detect the Cherenkov radiation emitted by the charged particles in the particle showers that are initiated by the neutrino interaction. So in this case, the particle interaction happened somewhere inside deep inside this blob, and then the particle shower was emitted from that point radially outwards of about a diameter of about 10 meters in size, and the photons radiating from it expanded all the way to hundreds of meters around the interaction vertex. So this is more or less a spherical event. And given a shower, we don't know whether it was made by a nu or a nu tau. And tracks. which also have a shower around the interaction vertex, but the final state product of the interaction of the neutrino with the nucleon also contains a final state high energy muon, which exits the interaction region and leaves a distinctive track of Cherenkov light as it ranges out for a kilometer in length or so. So whereas showers have poor angular resolution because of their more or less spherical nature, tracks allow us to point better due to the leverage arm of the muon to less than 1 degree, and that can use them to find sources. From those two kinds of events and other ones that are less common, we built 4 high energy, high level neutrino observable: the neutrino energy spectrum, the arrival direction neutrinos, the flavor composition, and the arrival times, which compare the arrival times of neutrinos with gamma rays possibly coming from the same sources. For us, what will be important today is the flavor composition, and that is the proportion of nu e, nu mu, and nu tau neutrinos in the diffuse flux that reaches the Earth. And the standard expectation, as we will see in a moment, is that we shall see about equal amount of flavor at the Earth. And deviations from that are interesting because they might mean it. So let's start predicting the flavor composition of high energy neutrinos at Earth. And for that, we first need to start by having a model of neutrino production of the sources. As I said, protons may interact with the environment, and nominally we expect the mesons that eventually decay to make twice as many nu mu as nu e. Those neutrinos get emitted, they propagate over up to a few gigaparsecs of distances to the Earth, and the initial number of nu e, nu mu, and nu tau produced change as a result of the fact that neutrinos oscillate in flavors, and therefore the expectation for the flavor composition at the Earth is different in general from the flavor composition at the emission point. Instead of dealing with the absolute numbers of neutrinos of each flavor, we actually deal with the proportion of nu e, mu, and nu tau, the total number of. So there's a number for each flavor between 0 and 1, and the addition of the 3 is to be equal to 1 because we normalize it. So we know then what the flavor composition is emitted at the sources, and we know how to calculate neutrino oscillation probabilities, which we know from theory. Then we can predict what the flavor composition should be at the. And of course, that requires us to know not just the flavor of the sources, but also the values of mixing parameters that control the flavor transition, which are, as far as we know, constants of nature that are measured by oscillation experiments carried out at lower energy we're dealing with here. And this is also where new physics can come in and modify the oscillation probability in a detectable way, essentially. So if we start again with some guesstimate of what the initial flavor composition is, and we assume that we know perfectly well the values and parameters that control flavor oscillations at this distance and at these scales, premixing angles and 1 CP violation phase, then we can make predictions for the flavor composition at the Earth. So let's start with a model of astrophysical neutrino production that is via proton interactions, creating intermediate pions, which decay into muons and nu mu's, and then the muons decay further into nu e's and nu bars. And I'm not distinguishing between neutrinos and neutrinos because experimentally IceCube does not. So that means that for every 2 neutrinos of the muon flavor produced, we produce 1 neutrino of the electron flavor. So we call that 1/3 nu e, 2/3 nu mu, and nu tau. And we can use one of these ternary diagrams to illustrate how that looks. So the ternary diagrams are such that any point drawn inside the diagram has coordinates that added up are equal to 1. In this case, this point lies at one of the axes, which means in this case the nu tau equals 0 axis. It has 1/3 flavor of nu e, 2/3 flavor of nu. And then we assume that we know perfectly well the values of parameters. We turn on the flavor oscillations, and the flavor composition at the Earth turns out to be very close to the center, close to 1/3, 1/3. That is the nominal expectation that we have for the flavor composition of high energy astrophysics. But we can start from somewhere else at the sources. For instance, if the sources have a very high magnetic field, then these intermediate muons that get produced upon the pion decay, they synchrotron cool before they get a chance to decay into high energy neutrinos. And so the only high energy neutrinos that we get come directly from the pion decay. And so we start with a pure nu mu flux at the sources, and that gives us at the Earth some composition that is slightly depleted in nu e. And in contrast, we could start with an exotic source that is producing only nu e bars from the beta decay of neutrons and neutron-rich isotopes. And in that case, once we turn on the flavor oscillations, we expect a enhanced nu e content, which you see. But so far, we have assumed that we know pretty well these mixing parameter values, which is not true. We know them experimentally from oscillation experiments. If we turn that on, if we account for that uncertainty, then those points, which are our 3 flavor composition benchmarks, become regions. And the more we allow the error on those mixing parameters to be 68, 95, and 99% in confidence, then the larger the regions of allowed predict flavor composition is at the Earth. And here you might already have identified a problem, because these three predictions of the three benchmark scenarios, when projected on the different axes, for instance, the nu tau axis, it turns out that they overlap. They give similar ranges, overlapping ranges of nu tau content at the Earth. So separating between them by measuring the flavor position at the Earth, I will say more about it in a moment, is challenging because the theoretical predictions are overlapping. Moreover, these three are just benchmarks. So if we now account for all possible flavor combinations at the sources and not just these three, then those three regions connect into a single bigger region, which is the region of allowed flavor composition at the Earth. If we account for the uncertainty in the missing parameters, and we account for the uncertainties in the initial flavor sources, and we assume that their flavor transitions behave without the influence. This is actually good news. On the one hand, that region is quite small, which means that if we have enough precision to make a flavor measurement at the Earth and that measurement turns out to be far from this region, then we will have discovered new physical flavor transitions, and there's lots of space in the flavor triangle for that measurement to be not a blue region. On the other hand, this also establishes the level of precision that we need to distinguish between different production mechanism sources. So we need to be able to to make a measurement that lies within standard physics only, lies within the blue region, but is able to separate between it. We want to learn about the astrophysics. Very well. So let's talk about measuring the flavor composition. Measuring it is difficult because, as I showed earlier, given one shower, we don't know if it was made by a nu tau. However, if we do see a track, then we know that it's very likely that it was from a nu. So in spite of that, IceCube has been successful at measuring the flavor composition. The first time they did it was in 2015. You can see that the best fit point lies on the axis no nu tau content, and there is a large error around. In 2018, the measurement actually jumped on the other side for the best fit value, but the error bars, their regions remained also large. Later, in 2020, IceCube started incorporating extra sensitivity to nu tau events separate, and they did it via looking for double bang events. So these are pairs of showers that are causally connected that will be coming from the interaction of a nu tau and then the consequent decay of the tau that gets produced in that shower. When they accounted for that, then the best fit point actually moved closer to the center of the nominal prediction for the flavor composition, even though the region of uncertainty around that remained very large. A similar analysis recently presented in the summer yielded also a large region, which is the yellow one that you hear, but it has the potential to become better once flavor identification techniques run on the same data are in. So it can become a closed control loop in the near future once the analysis is finalized. But beyond that, what I want to call your attention to is this new measurement. This is the measurement of the flavor composition recently reported by IceCube using events that are starting at an energy that is typically lower than the ones that are used for flavor measurement, so 1 TeV. And it is the first time that IceCube reports a measurement of the flavor composition that is non-zero at 68% level for all of the flavors. So finally, the contour is starting to close, and it is centered on the center of the triangulation. So there's no apparent large new flavor composition. Now, that's about the measurement of the flavor composition, which requires more statistics because you want more showers and more tracks, but also better distinguishing between tracks and showers and better distinguishing between nu tau generated events. On the other hand, there's also parallel progress in the measurement of the mixing parameters that control the size of the allowed theory regions that we showed earlier. So the current situation is more or less what you see here in 2020. It hasn't changed much since then. Once hyper K measures theta to 3 better, those regions are going to be going to shrink in the nu tau direction. And once Juno measures theta 1, 2 better, they're going to shrink in the E direction. So by the year 2030 or 25, the combined measurements of the mixing parameters by hyper K, Juno, and also Dune are going to turn those predictions were regions into virtually points. And at that point, at that stage, distinguishing between them, given also the improvement in the measurement of the flavor composition, is going to become a lot better. Very well. So what can we do with the measurement of the flavor composition at the Earth? The first thing we can do is go back to the sources. And by that I mean we can use the information, we can use the measurement of the flavor composition at the Earth and the knowledge of the neutrino oscillation parameters to undo the effect of the oscillations and try to infer what was the original flavor of the neutrinos as they were produced by the source. And by that, to indirectly learn about the sources and about the physical conditions in them. So what we do is we will take the different measurements of the flavor composition at the Earth. We will perform a Bayesian analysis undoes the effect of the oscillation, and I will show you what is the result for the inferred amount of nu E content at the production, at the sources. And I'm just using nu E as an example. So if you start with an old measurement in 15, which is very large, then once we undo the effect of oscillations, it turns out the referred value actually is close to 0 nu E content at the sources, which is what we would expect if neutrinos are produced only from the direct ion decay and the muons are damped by synchrotron losses. Now, if this is a projected measurement of the flavor composition, if the flavor composition were like you see here, centered at the center of the triangle, the pion decay nominal expectation, and with about this size, then the method that we proposed back then would actually be able to favor a value of nu E that is compatible with 1/3. It's what we would expect from the production of neutrinos by a pion decay. And what I show here is not the actual result from data. It was back then a projection, but it turns out that once IceCube did this analysis using real data earlier this year, it has found a region interval of Fe at the sources that is compatible with what we predicted there. So the most likely value so far is around 1/3 for inferred from current data, with an uncertainty that is similar to the one here. And of course, if one gets better at measuring the flavor composition at the Earth, and also the mixing parameter values are known better and better, one can more precisely infer the flavor composition at the sources, which is what you see here. Eventually, one combining many different detectors and with massive improvements in the knowledge of the mixing parameters, measure the flavor composition at the sources with a percent level. Very well. So far, I have assumed that the flavor composition as produced in the sources is independent of neutrino energy, so it's a constant. And that might not be the case. What you see here is more or less the current situation up to just before the results from IceCube shown earlier this year. So we have the 3 benchmark scenarios here: the pion decay, the muon damped case, and the neutron decay. And I want to explore one case. The flux of neutrinos we see here in the y-axis changes abruptly to the different flavors at some hand-picked value. In this case, for this plot, 1 PeV. So at that point, the synchrotron energy losses turn on, given the size of a mock magnetic field in the sources, and the nu E content drastically falls, while the nu mu and nu tau content drastically increases the flux. So the question is, would we be able to see the transition between a low energy composition where there's no such effect and the 3 flavors are more or less 1/3, to a high energy composition where there's a synchrotron losses that signal that there's a depletion in the nu E content? In the current data, the answer is unfortunately no. It is not possible. So what we did here was a repetition of the analysis that we did earlier, but now accounting also for a break in that in the flavor composition. And it turns out that the data does not support a difference between a low and a high energy difference in the flavor composition. One can make, of course, predictions for the future, and these are very extreme predictions. So this is roughly by the decade of the 40s, using everything that we can throw at it. So it's both all types of different neutrino events put together that as detected by IceCube, by its planned successor, by the bicycle detector and the game trainer detector, and all the detectors that are being planned currently to detect high energy structures. And even in that case, the separation between the 2 high energy and low energy flavor compositions can be achieved only at the level of 1. So this is a very difficult measurement. Let me just close by saying that it's been a spectacular 10 years since the discovery, 12 years now since the discovery of astrophysical neutrinos. We went from having the first predictions to having the first PeV neutrino discovered, the hints of the first sources, the first test of neutrino physics. That's where we are now. We're planning how to get to where we want to be 10 years from now, which is discover discovering or at least seeing more EEV neutrinos, making the first precision test PEV neutrinos once we get to better statistics and better reconstruction techniques, and maybe going into the first test of the kinds that have shown, but neutrinos 1,000 times higher. So what we're working on now is how we get from here to there. And what I showed you today is what the current state of affairs is, but there's lots of ongoing progress for how we improve every single axis in order to get better at all this. So thank you, and I'm happy to discuss with you offline.